Hello everyone, welcome back for another podcast. So in today's podcast I thought I would go over this table, kind of discuss the joinery, why tables like this have the joinery and the structure laid out as such. I am pretty much finished with this, but before I put the thing together and stain the legs and everything, as I said, I just wanted to go over a bit of the construction of it. And for those of you that are interested, this spalted sycamore is going on top, so I'm really looking forward to getting some finish on this. I did put some water on it just to raise the grain a little bit, and obviously just to see how it's going to look, and I think it's going to look absolutely gorgeous once everything's sanded up. So the basic construction of this table, for those of you that are listening and not watching, this is basically a small table, an end table or a side table that sometimes gets called here in the UK. So this arguably could be called a shaker style, and I wouldn't disagree with that. It most likely, would fall under the category of a shaker style table. The only difference with this is that on the tabletop I am going to be leaving the veiny edge on, and as far as I'm aware, typically on a shaker style table it would all be square edges. Obviously some of them had a round and a little bit of a bevel or a taper. The shaker design goes back I want to say the 1800s. I don't think it goes back any further, but then again I'm not very up on the shaker history. The only thing I know about the shakers is that they were very competent builders, building houses and building furniture, and they're very well known for the furniture building. I do like a lot of the furniture, the designs, very simple, sturdy, stout pieces, and there's quite a lot of the chairs and the tables still, fine examples existing today. So with that being said, obviously they didn't invent the construction or this type of construction. And what I mean by this type of construction is the end grain going into the long grain. So again, I'm not 100% with the history, but I think this sort of construction come about, I think maybe in the 16th or 17th century. And basically this construction was to help with wood movement. So when they were making doors, and this is again, this isn't gospel truth, this is what's in my brain. I've probably read this somewhere. So this sort of constructions came from doors. So basically when they were putting doors together, they would have the planks of wood, or I believe they used to use slabs as well. So the slabs or the planks of wood. So the problem with that is that when they actually fit them, whenever they fitted them in the year, there would be problems in the summer and then going back to the winter again. So there would be contraction, expansion, contraction, expansion. So obviously that's gonna create problems. So despite popular belief, wood does actually move lengthways, or grain, it does actually get bigger and shorter. It's very minimal. It's barely noticeable, so I tend not to worry about things like that, and neither does anybody else. That's why this construction come about. So going back to the doors, obviously with the width or going across the grain, that's where the most movement happens in wood. So the problem with this being that, as I said, during the seasons, the change of the seasons, the doors were either jamming or they were becoming loose, letting letting the weather in, letting the cold in, rain, and most likely insects and small mammals, things like that. And so entered this sort of framework. So the way this kind of works is that, let's just say we had a door, for instance, or even a table. So one of the main concerns, especially with a door, let's just say, would be the expansion if they were using boards, you know, that were running long ways, long grain from the floor, from the threshold to the head of the door. So they would expand on the two rail sides, or rather the whole way across. So it's quite clever how they've solved it. Basically, what they've said is we'll put a rail one side, we'll put a rail the other side, and then we will put our head, and we'll put our bottom rail. And basically, with the bottom and the top, the head, it's going end grain to edge grain. So in contraction and expansion, all they have to worry about, or all we have to worry about as woodworkers, is this side and this side. So you're eliminating all of this potential movement because you're going end grain to side grain, if that makes sense. On this particular table, if the side rail was in the same orientation as the legs, or the leg grain rather, would have a lot more to worry about, obviously, with contraction and expansion. And again, this would be problematic for the drawer, providing the drawer was built correctly, of course, because you would actually see it would actually push itself out, and you would be able to push it in depending on the season, the humidity, and so on and so forth. So obviously there's a reason why on the rails we do actually have the grain running from leg to leg, rather than the grain orientation going in the same orientation as the legs do. So most will know, although I do still see it occasionally, if you have a rail and you were to cut it, and the orientation of the grain was going in the same way as the legs, you could pretty much punch that in half. You know, go right in the middle and give it a good old wallop with your fist. You could probably put it through quite easy. That's because there's not a lot of strength in the width of the grain going across the grain, rather with the grain. That's where the structural support is. Obviously, if you're doing it in short pieces, you know, maybe 170 mil, you know, going up to 1 foot, it's not too much of an issue. But obviously, when you start getting past that, the wider you go unsupported, it's just going to snap. And obviously, you've got the problem of contraction. So, you know, again, that's why that is done. Moving on to the mortise and tenon joints, again, mortise and tenon joints, they're a really good, strong joint. There's a reason they get used, and that reason is because if they're done properly and the furniture is looked after, you know, there's still examples of furniture with mortise and tenon joints and dovetail joints dating back to the 17th century. It's a no-brainer. If you want something to last, you know, it's always better to use traditional methods. That's my personal take on it anyway. So these particular mortise and tenon joints are mitered, which basically means that when the corner meets, they've actually got a miter. So expanding on that a little bit more. So basically, when the two rails go into the leg, it's got a mortise in the leg, and it's basically in the shape of an L, if that makes sense. So the problem with this is that they're not going to sit completely down. So there is a couple of ways you can get around this. You can basically cut a notch out, you know, like a bit of like a castle joint sort of thing, or you can miter them. So with these particular ones, I opted to miter them. Bang in the corner, the two miters do actually meet each other. And this does add a little bit of structural strength, but it's not where all of the structural strength comes from in a mortise and tenon joint. To understand the mortise and tenon joints, you've got to kind of understand the anatomy of the mortise and tenon joint. So basically, a mortise and tenon joint, or at least the ones in this mortise and tenant joints, the one I've used on the table, basically they will consist of shoulders and the tenant itself. So these tenants that I've put in here, these are actually bare-faced tenants. Bare-faced tenants is kind of what it sounds like, I suppose, in a sense. So basically what it means is that we've still got two cheeks of the tenants, the back and the front, and basically it'll only have shoulders on one side of the cheek. So on these particular mortise and tenant joints, the bare face side is actually inward, and the shoulder side is the section that's visible to the eye. So obviously it's a lot neater because I've got the shoulder buttoned up against the legs. So as also with these ones, I've got side shoulders on both sides. So one of them is actually quite a lot bigger than the other one. So the top section shoulder, I forget what that is now, but it was substantially more than the bottom. And the reason for this is that when you're making mortise and tenant joints and you're fitting the joints, there's always that possibility when you're wiggling the tenant into the mortise, it can actually be quite common for you to damage the top and basically push the top out, because there's not a lot of end grain. End grain's quite strong, but when you're applying pressure to end grain, and there's not a lot of end grain, it can break quite easily. So that's what I actually done with that. Another way to get around this, and which is quite common, or used to be quite common, is that they would actually leave maybe like 2 inches on the top of the leg. So you would fit your tenant, you would get everything glued into place, maybe put a draw bore in it, and then trim it to your final size, which obviously makes sense. I didn't do that. I just brought them down a little bit more, and I think it's going to be better, just in case there's any sideways stresses that stress the leg. I just think it's safer to do that in case the glue should fail. The glue shouldn't fail in these. Also, I have got some draw bores put into them, so I think personally this should be around for a long time. It'll probably outsee me, to be honest. To try and understand how the mortise and tenant joint works, I'm going to try to explain it. And one of the keys to the success of the mortise and tenant joint is basically the shoulders. The shoulders, they kind of make or break the tenant, if that kind of makes sense. So if we can imagine a tenant without any shoulders, so we'll put it in the mortise hole, we'll glue it, and we could even stick a couple of draw bores in it. That would probably be okay. It might not look very good, depending on how precise you got your tenants. But I think over time, because there's no shoulders, with the racking, if it's on a table, let's just say, with the racking, it is eventually going to start to swivel in the mortise and tenant joint. And obviously when it starts to do that, it's game over. And it's only a matter of time before that section completely fails. So in comes the shoulder. So if we add a shoulder, even if we just add one shoulder, that means we've got what was said before. Basically, it's glued into place. It may even have some draw bores in it, but as extra support, it's actually got the shoulder button against butting against some sort of an edge. And obviously when that's racking left and right, up and down, whichever way it may be going, it's got a lot of support because you've got the end grain of the shoulder that's butting against that. The underside of the table, it has got a shoulder on there, and basically this is serving a purpose as well. Obviously you've got the ones at the side, obviously they're serving a purpose as well, but with the ones on the underside, they're gonna help for the table legs to resist to come in against each other. And it's the same again. Let's just say this is in a house, someone trips, kicks the bottom of the leg, maybe it's up against the wall. Now if this has got shoulders like all the way around, it's probably going to do very well. It's going to fare very well, although you shouldn't really be going around kicking tables, but obviously in an accident situation things do happen. So if it was a mortise and tenon joint, I wouldn't worry too much about it. If it was something, let's just say maybe you got from IKEA, it's most likely going to be broke. So like I said, with the shoulders, because the shoulders are in, and actually hitting the leg, it's going to resist that sort of movement. As I said, one of the key features to making the mortise and tenon joint work so well is the shoulders, and primarily this was the reason what I chose a bare face tenon for. You could argue that it would have been stronger if I had to put a shoulder all the way around it, and you wouldn't be wrong there. I wouldn't argue about that. However, with the thickness of the material and basically just the construction of this, if I had have done that, the shoulder itself, it wouldn't have been very big, and I would have had to have reduced the tenant. So the way I've got it is that I've got a 1/2 inch tenant in there, which it's 1/2 inch, it's like 12 millimeters, so that's quite a substantial amount of tenons thickness that's into the leg, which I'm happy about. And with us doing the bare face tenons, I was able to actually get quite a decent amount of shoulder that's making contact with the leg as well. So again, I'm happy about that. My logic is that because I've done that, this is going to survive a long time. It's going to survive a lot of bumps and whatever else it may occur in its lifetime. I mean, who knows, maybe it won't, but that's the logic in my head. So now we've got the front rails. So arguably this is probably the weakest part of the table, because there isn't substantial amount of shoulder. So obviously on the side rails and the back rail, we've actually got shoulders running with the length of the leg, which obviously gives it strength for the legs to come in on themselves or to split out on themselves. You haven't got that at the front, obviously, because there's going to be a drawer fitted here. So you will actually get a little bit of support when the drawer is actually inserted into the table, because if there is some sort of racking left to right, the framework should hit against the drawer, and the drawer should help, for it not to rack too much. But same again, this is arguably one of the weakest parts of the table for that reason. For the construction of this, we have dovetails at either side. I did stick a drawer bore in these. There's a drawer bore in every single joint on this. So the logic of this and why this is done, because this is a dovetail going into end grain. Obviously the tails are coming this way. So basically this is going to stop the table from spreading. Obviously that's what a dovetail does. It's the same sort of principle in a drawer. You always put the tails on the side and the pins on the front, so over the years of that drawer being pulled in and pushed, pulled, pushed, it's it's obviously it's the design of the dovetail. So when you're pulling it, you're pulling against the fat end of the dovetail. So you know, mechanically it's strong, and it's the same sort of principle with this. But what I did do here, and I've done it very badly, where the dovetail fits into the end grain of the top of the leg, the material was thick enough, so rather than rip it all the way down, what I've done is I actually tried to make contact with the side rail, which I didn't do. If you're watching this on YouTube, you'll be able to see that there's about a 1mm gap, and I'm able just to get my fingernail down there. So I would have preferred that to have, you know, made contact with this. Another reason for this is that there's more glue area for me to glue, you know, the two side grains. Given that it is at 90 degrees, but you know, it is better, in my opinion, to be adding glue to that. Ironically, because I'm an idiot, you'll be able to see the corner missing here if you're watching on YouTube. And that's basically the round over. Obviously I rounded all the corners over on the leg, and I got a little bit gung-ho. I got a little bit happy rounding things over. So same again, I mean, I would have preferred that to have been square and a nice tight fit. You know, I would have been a lot happier with that. As I said, this is glued and it does have a draw bore in it. It probably wasn't necessary, but like same again, I thought, you know, I want this to last a very long time. Whether I keep it or sell it, you know, it is a bit of peace of mind for me. So the draw bore does, I think it goes down maybe 2 inches from the top. So, you know, the draw bore is beached, so it has given it quite a lot of strength. You know, it'll be a job to actually pull the thing apart if you should ever try to do that. The bottom rail, this is just simple mortise and tenant joints, and this comes in, I think, it comes in about 20mm, I believe. Same again, there's a draw bore going through here. So basically, you know, the drawer is going to fit into here. I have still got to make some rails that the drawer is actually going to slide onto. These are just going to be fit into place here with some screws. I may possibly glue them, I'm not overly sure yet. So before I glued this together, I did actually add some grooves into this, and basically these grooves were intended for some buttons. Basically the buttons fit into here, and the screw goes through the button and fixes the tabletop in place. And what this allows this to do is it allows the top to contract and expand, basically move during the seasons without fear of anything splitting, or i.e. the top splitting. So I did actually screw this up. So I went to the trouble and I made the buttons, and when I actually put the buttons in, it dawned on us that the material thickness of the buttons is actually thicker than the material at the front of the table. You know, where the drawer fits through, where the dovetail section is that goes in the legs. So the buttons were actually thicker. So the problem with this is that I've actually made the groove specifically for that thickness of material. So I literally couldn't take any more off the buttons themselves. There just wouldn't have been enough material. I wouldn't have been happy with it. It would have been quite easy to, like, literally, you know, pull the top of the table off. So I mean, at this point, everything's glued up, but, you know, traditionally, that's what would have been used, you know, the groove in it, and then, you know, they would have just used the buttons, the tabletop fasteners, just made out of wood. These were made out of beech. The issue with this is that I can get the figure of 8 ordered, from Amazon, but it's going to take 2 weeks for them to get here, which I don't want to do. I don't want to wait that long. So the only other thing I can think of doing is either make some, again, which I don't want to do. I kind of want to get this wrapped up, or put some pocket hole screws in it. So the issue with the pocket hole screws is that I'm worried that there might not be enough movement, you know, in the screws. The screws might not allow like enough movement for the tabletop itself to move. So obviously when the framework, you know, has been put together, been glued, screwed, draw board, whatever you're going to do to it, you're going to be ready to put the tabletop on. So when the tabletop's actually secured in place, the tabletop is actually going to help with a planned diagonal force. So if there was ever any force diagonally on this, and the framework itself wanted to collapse in on itself, like from a bird's eye view, obviously the tabletop is going to help to prevent that, providing that you've got enough fixings in it. But same again, you can't go crazy putting too many fixings in the top, because you still have to allow for that contraction and expansion during the seasons, or you know, there's a good chance you're going to end up with big cracks in the top of your table. One thing I did forget to mention about the legs, and this is really good advice for maybe the beginners who have started making furniture and woodwork in general. It's always good practice, whether it be table legs, chair legs, anything that's going to see a good amount of stress or downward force, you should be looking for straight grain. So you know, for those that don't fully understand what I mean by straight grain, is grain that's running really straight from the top of the leg to the bottom of the leg. So what this is going to do, this is going to add like a lot of strength. The structure of the original wood is really going to be strong, and it's going to take a lot of downward force. So if it wasn't straight, this particular wood, you know, if the grain wasn't that straight and the grain was actually running out, let's just say halfway up the leg, it was running out, the grain was running out. It's not a given, you know, it's not 100% that will break, but if it ever does break, it's going to break there because the grain's running out. So it is actually something to consider. You know, same again, if it's a chair, a table, anything like that, you should always try to get the straightest possible grain, and that's going to give you optimal strength. So for me, the chances of this leg breaking, it's next to zero. You know, with a downward force, I ain't concerned about this. So it is actual peace of mind that if you're making this to give to somebody as a present, maybe a member of your family, or if you're actually going to sell it, it's a peace of mind. At least it is for me, because there's a good chance I am actually going to sell this table. I may keep it, but there's a high chance I'm going to sell it. So that's peace of mind for me. And it's the same with everything. You know, you could argue that you've glued this together and it doesn't really need the draw bore in. You know, you could argue that, but the way I look at it, I've built this properly, and I've went that little bit extra to put the draw bores in and made sure all the grain's good, giving myself thicker tenons, giving myself thicker shoulders, and that's peace of mind for me. And I don't have to worry about a friend or a family member coming back and saying, you know, the table's broke, or I don't have to worry about a customer, you know, saying, listen, I want me money back, the table's broke. I don't have to worry about that. As I say, this table should last a long time, not because I've built it in general, but because I've used traditional mortise and tenant joints, and the traditional style of putting these things together. And as I said earlier on in the podcast, it's tried true, and there's examples of this sort of structure still surviving from the 17th century. So 300 years, it can't be all that bad, can it? So for those of you that are actually wondering the sizes of this table, so the length of this table is 32 inches. That's just shy of 14 for the width, or the depth if you like. And the height is 27.5 inches, minus the top of course, and with the top one it is 28.5 inches. So I'm going to get back to making this table because I'm very eager to get this finished. I'm really looking forward to seeing how this spalted sycamore is going to look. So I'm going to leave it there for today, guys. Until the next time, I shall see and speak to you guys later.